All right, class, today we're going to learn about quantum numbers and how to assign them to electrons. We're also going to determine the electron configurations of neutral atoms and ions with 80% accuracy. We're going to revisit some of the rules for electron configurations from honors, and we're also going to look at orbital theory. This pairs well with quantum concepts 8b and 8c. So, it's been a while since we've talked about orbital theory in regards to electrons and how they're placed in the atom. We're always viewing an orbital as an electron cloud. The name orbital is kind of a misnomer. We know back in the day we used to have rings when we're looking at the Bohr model. We know those rings aren't really true. We know they don't really exist. If we're looking at an atom, a lot of people tend to look at the atom and visualize this, but the issue with this is that it shows very distinct levels when that's not actually the case. We know it's kind of like a gradient as we go through. This representation here of electron density is actually fairly accurate. You have areas where it is more likely to find an electron based on Heisenberg's principle. Heisenberg's principle, the uncertainty principle, states that you can know either the position of an electron or its velocity, but not both. Think of it like taking a picture. If you took a picture of the atom, you'd be able to see everything in the atom at that moment, but it's really hard to figure out how fast things were going by looking at that picture. All right. So an orbital, it's the region in space where there's a 90% probability of finding an electron. All of this is based on wave functions that were calculated by Schrödinger. Gets really into the physics and the differential equations, and it's a little wild when we get into wave functions. Just know that those wave functions do result in different shaped orbitals, and those orbitals help us determine our orientation in space. So we know we have S, P, D, and our F orbitals. The S and P orbitals are the most crucial. We've definitely looked at those before because they are the ones responsible for our bonding. When we have the overlapping of our S and P orbitals, that's when we get bonds forming. You don't typically see that as much with the D and F orbitals, but the D and F orbitals do hold plenty of other electrons in our atom. Okay. When we're looking at these orbitals, because they're all oriented in different ways in 3D space, we can assign some sort of quantum number, or in other words, an address, to particular electrons in that region. So if I, for instance, thought that there was an electron right there, somewhere in here on this left side of this orbital, I would be able to determine based on, one, its orientation, two, which lobe it's in, and also what energy level, and tell you exactly where that electron will be to, 90% certainty, right? We're looking at that particular region. So that's the idea behind all of what we'll be doing today. It's looking at the probability of finding an electron and how can we identify those things with some sort of code or address. So first things first, I just wanted to review your electron configurations and all of those things. So when we're talking about electron configurations, we know we have different energy levels. Let's just look at the first 4 energy levels because they're the most relevant to us right now. We know the first energy level can only have an S subshell. Now, if you remember looking at the boxes, if you had the 1s, you thought about the boxes, you got different boxes and everything's at a different energy, right? You got 2s and 2p. Well, when I ask number of orbitals in the sublevel, I'm talking about the number of boxes here. Each box is an orbital. So if we go back to that s orbital, there's only one type of shape there, and it's a sphere. So we have one orbital in that sublevel. And in each sublevel, we can have a maximum of 2 electrons. If you remember, they were one with the spin up and one with the spin down. So arrow pointing up, arrow pointing down. Okay. When we look at the p orbital, there are 3 different possible shapes or orientations of that orbital shape, and therefore we end up getting 3 different boxes. So we know that in energy level 2 we can have a 2s, which is the same, 1 and 2. We also can have a 2p. There are 3 different shapes in there, or orientations of our shape, and we can get a total of 6 electrons in the p sublevel. In total, we get 8. This makes a lot of sense because the s and p makes up your valence electrons. That's how we get our octet rule. Like I said, those are the ones that will be responsible for bonding. So S and P, and we'll revisit this next unit, S and P partake in bonding. Okay. When we get into the higher levels, we end up getting a D sublevel and we get an F sublevel. So the nice thing is that everything is the same for the S and the P. So we can fill those out. D, we've got 5 different shapes, and therefore, not 5 different shapes, but 5 different orientations, and therefore we have 5 orbitals. And 5 times 2 is 10. 10 possible electrons can be there. We can have up to 18 electrons in that level. Again, we only can have a max of 8 valence electrons, but we do have 10 electrons in that expanded octet for the d orbital. All right. Then same thing, we get a 5 and then a 10. And then with F, we actually have 7 shapes. 1, 2, 3, 4, 5, 6, 7. So since we have 7 shapes, we have 14 electrons for a total of 32. Okay. So the reason this matters, we want to be able to assign quantum numbers to our atomic orbitals and to the electrons in those atomic orbitals. So we have the principal quantum number. Principal quantum number is n. This represents our shell. I say our shell, that's a terrible word too. Shell, I'm talking about our rings. If we're talking about the rings, even though we don't have rings, but if we're talking about the rings in our molecule, we've got our first ring, n equals 1, second ring, n equals 2, third ring, n equals 3, etc. When we're looking at our electron configuration code, say we've got something 1s2, this refers to our n. We also have the angular momentum quantum number. The angular momentum quantum number represents our subshell. By subshell, I mean S, P, D, F, and we start by assigning S a value of 0. So it's represented by the letter L, and we always start by assigning it assigning 0 to S, and then we work our way up. So we assign 1 to P, 2 to D, 3 to F. If we went up to G, we could start doing a 4 or a 5 for H. It just keeps going up and up and up. There are more orbitals than just S, P, D, and F. Like, it actually goes in alphabetical order from G on up. So the interesting thing is those things have a range. So the range of L is n to the minus 1, which makes sense. However many rings we have will dictate the number of orbitals. We also have the magnetic quantum number. So the magnetic quantum number is the energy shift. So if we're talking about energy shift, we're talking about, in simpler terms, number of boxes in an orbital. So we know that each of those boxes, if we looked at those boxes separately, so say we're looking at the p orbital. Say we got some p orbital here. We know we have 3 different boxes in here. The energy shift that it's referring to is which of the boxes? What box is it in? Tell me, what's in the box, right? So that has a range of -L to L. The reason it's -L to L is based off of the suborbital that we have. So with P has an L value of 1. So its magnetic numbers would be assigned to each box, starting with -L, going through 0, and then working to +L. So any electron that's on the box in the far left would be assigned a -1. Anything in the middle would be assigned a 0, and then everything to the right would be a 1. The last number is the spin number, spin projection. You'll notice that there's only two possible values, -1/2 and +1/2. If you think about your electron configurations, oh, you got an up arrow. That's +1/2. Oh, you got a down arrow. That's -1/2. And that's it. This is literally our way for identifying specific electrons and their locations. We know that electron configurations as a whole, the 1s2, 2s2, 2p6, etc., can tell us the electrons in total, but if we want to look at a specific electron, we need to use quantum numbers. So it lines up fairly nicely. If we were looking at the 1s electrons, we know that its first quantum number would be equal to 1 because it's in level 1. We know that s orbital is assigned a 0 for L, and then we know ml is equal to -L to +L. If L is equal to 0, then ml is just 0. And then you just have to assign a spin to which electron it is. So let's do an example together. Let's look at something like, let's look at fluorine. We know fluorine has 9 electrons. If you do that configuration, you got 1s2, 2s2, 2p5. And say we wanted to look at our p region. We know that when we fill them, they get filled this way, and we get left with something looking like this. What if I wanted to know the location of this particular electron? Okay, well first I have to look at what level it's in. This one's in my 2p level, right? This one is in my 2p level. So I know n is equal to 1. I'm going to write in a different color because that's hard to see. I know n is equal to 1, or sorry, n is equal to 2 because it's an energy level 2. My first quantum number is 2. Then I do a comma. Then I have to identify which orbital it's in. It's in a p orbital. If I look over here, p is assigned a value of 1. So 2, 1, and then another comma. I know that my m sub l, I have to assign that to my box. So I've got -1, 0, and 1. Which box is that electron in? It's in -1. Okay. And then is that electron pointing up or down? It's pointing down. So my set of quantum numbers for that particular electron would be 2, 1, -1, and -1/2. Not too bad. I'm positive you can do it. Go ahead and tell me the quantum number for this electron. All right, that should be pretty straightforward. That one would be 2, 1, +1 because it's in the third box this time, and it's pointing up, so it'd be a 1/2. You only had to change your last two numbers. I made it kind of easy for you. All right, let's move on. This is just a good recap and summary of everything. If you want to take a look at this, go ahead and pause, breathe it in, digest it, get used to it, and we're moving on. So we need to be able to write electron configurations for our elements. I'm going to make it easy for you. The filling order, you remember back in Honors Chem we had that filling diagram, the kind of Christmas tree looking thing, or it might have been like a giant bunch of squigglies and it went like, started up here and just like went, whee! Yeah, we're not going to use that. The reason why is because the periodic table tells you itself. If you look at the way the blocks are set up, you've got 1s, then you've got 2s, then you've got 2p, then you've got 3s, then you've got 3p. We know we fill the 4s first, then we fill 3d, and then we fill 4p. Well, that's convenient. And then we fill 5s, and then we fill 4d, and then we fill 5p, right? And then you keep going and going. Now, when you look at the intertransition metals here, you got to go to 6s first, then 4f, then 5d, 6p, back to 7s, 5f, and then 6d. That looks a little crazy, but the periodic table honestly is set up that way. If you looked at the expanded periodic table before, if you look at the periodic table, this is what we're used to seeing. If you've ever gone to p-table and clicked on wide, oh, look at that. They put all the lanthanides and actinides in the middle in between there for you. Yeah, so when you go from 5s to 4d to 5p to 6s to 4f, it makes sense because 4f's right there in between. And so it just keeps going in order. All right? That order matters. Okay, moving on. So, Pauli exclusion principle, let's recap. We've kind of already touched on it. No two electrons in an atom can have the exact same energy, and no two electrons in the same atom can have identical sets of quantum numbers. So, in other words, you can have one pointing up, you can have one pointing down. Okay, simple enough. The Aufbau principle. Electrons always fill the lowest energy first and then move up to the highest. So this means that electrons will enter the first energy, then second, and then keep going, right? So just like we saw before, we fill this way. The next rule we're going to cover in a minute is going to explain what I'm doing here. I spread all my electrons out in my p orbital before I start pairing, okay? That is Hund's rule. Electrons do not pair up until they have to. Remember, electrons are negative. They have repulsions. They don't like to be near each other. So, for that reason, we can start pairing things up as normal. But once we get into the same energy level and multiple electrons can be in that energy level, we like to spread out as far as possible. So, everything's going to fill the boxes. And then once each box is filled with at least one, then we can start pairing. Now, one of the things that messes people up a lot is when we get to this 3D level. So I'm going to go ahead and fill this out all the way up to the 3D. And this will help you conceptualize some things. One of the quest questions when we start doing these is actually about an exception. When we look at exceptions, the 3D orbitals always mess people up. And it's because of stability, and we got to look at stability and what that means for us. Okay? So, say we were to have a configuration that looked like this. All right. When we look at this, we got to remind ourselves about the nuclear distance. This technically means we've got 4 different regions here. We got 4 rings. You've got 2 electrons in this outer ring here, and you've got just so many in that 3rd ring that it hurts. But still, we're not quite complete in our 3rd ring. We can still hold a few more electrons in that 3rd ring. If we look at stability, and we look at how these 4s electrons are paired, even though they are the lowest energy level first, and we would fill them first, if you end up in a position like this where you have 4 electrons in your d orbital, most often, this electron in the 4s moves down to the 3d to complete or half fill that d orbital. And the reason why it does that, you have to remember about the internuclear distance. If we're looking at the distance between our nucleus and our outer electron, the distance from here to here is a lot greater than the distance from here to here. And I know that's obvious because I didn't really draw to scale, but things in the third energy level are a lot closer to the nucleus than things in the fourth energy level. So sometimes they rearrange and break the rules, especially when you're looking at transition metals, because they can spread out more, they can get closer to the nucleus so that it maintains the attraction. It happens fairly frequently. So be careful of that when you're looking at the transition metals and getting into the d orbitals, because you may see a rearrangement there. You may look at an atom like silver, for instance, and see that it does not have a typical electron configuration that you would expect. If you looked at where silver was in the periodic table, you'd expect silver to be, let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. You'd expect silver to be 3d9, but in actuality, that 3d9, that's got one extra spot there, and if you have a 4s2, that 4s2 electrons, these are going to repel each other. One of these is going to move over and make that a full shell, 3d10, and then 4s1. It's just how they rearrange, and it's just to make it more stable. It's not for every single atom in that region, but case-by-case basis, just be sure you're aware of the exceptions. Okay. While I'm on the topic of that rearrangement, before I forget, sometimes that 3D rearranges with the 4s, and that actually can contribute to the number of valence electrons that a transition metal element wants to give away. And that also helps explain why we have multiple charges for our transition metals. So iron, we know, can have a +2 charge or a +3 charge, because it can lose either 2 valence electrons or 3 valence electrons. It could lose the 2 valence electrons here and become a 2+, or it can also lose this one because a half-filled 3D orbital is more stable than one that has 6 in it, because you still have that repulsion going on in this region here. So just think about that. I've got good news for you. You don't have to write out that entire thing. Let's use the configuration shorthand. So if you look at the periodic table, we know the 1s level is completely filled. We know the 2s level is completely filled. And we know level 3 is not completely filled, but that's okay. We can still look at the S and P of that, and we know that's completely filled. If we wanted to use a shortcut, let's find iron on the periodic table. All right, here's iron. Let's find the previous noble gas. The previous noble gas, if we go back, is argon. We know that the only difference between argon and iron in terms of electrons, iron has 8 more electrons. You can use the noble gas of the previous level to write a shorthand. You can condense this and say argon 4s2 3d6, and that would give you your noble gas shorthand. That would be a valid answer for iron. Okay. A brief mention of diamagnetism and paramagnetism. Diamagnetism means it's not magnetic. When you have a diamagnetic atom, we're looking at things where all of the electrons are paired. When you put it in a field, if everything's paired up, there can't really be any interaction. But if it's paramagnetic, that's when you have electrons, single electrons that are unpaired. Those things tend to interact with a magnetic field. Okay. So Practice writing the ground state configuration for the following. Please enter them one at a time on Play Pause. So A for sulfur. Cadmium, Cd. Iron, Fe. Bromine, Br. Okay. If you use the shorthand, that is okay. Sweet. All right, the last thing, we got to look at ions. So ions, I'll do the first two with you, and then you do the last two on your own. When we look at ions for the ground state configuration for the ions, we have to remember that this is at the point that they've either gained or lost electrons. So we know that sodium typically has 11 electrons. If it becomes positive, it's lost 1 electron. It now has 10 electrons. This is the same as the noble gas configuration for the previous element. That's why we use the noble gas shorthand. So if you look at sodium, sodium's previous noble gas is neon, which has 10. So you've got just neon. If you want to write that out, 1s2, 2s2, 2p6, boom. All right. Same thing with fluorine. Fluorine starts with 9. It becomes a -1, which means it gained an electron, and becomes 10 electrons. So -1, +1. Oh, look, it's still neon. What are the configurations for zinc? Zinc 2+ specifically. All right. And then cesium 1+. That is all for today.